Thanks for the chance to talk about this. Like Sandy was saying, we're going to talk a little bit about our hybrid and OpenVPX SpaceVPX payload processors that are using the GR740. I'm Paul Graham. I'm representing a much larger team, of course, here at Los Alamos. And I've highlighted a few of the engineers' names, Tony Nelson, Robert Merle, and Justin Tripp, that are helping specifically with a lot of the hardware and firmware designs. All right, get my slide to advance. All right, so Los Alamos National Laboratory, of course, you may be aware, we're in the great state of New Mexico, lots of sunshine and snow sometimes, and we've been doing space for more than 50 years, some for national security missions, some for scientific discovery missions. And a lot of that experience has driven, our use of computing in space. And, the Leon 4 is the third generation of Leon that we've worked on. We've got Leons running from Leo to Geo, and some running around on Mars right now. So a fair amount of experience there. And we'll talk a little bit about some additional things here with our efforts over the last many years. Years ago, especially early on, we did a lot of full custom design work, and in the last 20 years, we've benefited quite a bit from leveraging commercial standards, compact PCI, micro TCA, and now VPX for developing, producing, and deploying our systems. I think in some cases we've certainly seen as much as a 2x productivity benefit, due to design reuse, being able to leverage a lot of commercial infrastructure, not having to bring up everything ourselves, and having more hardware available in parallel for development and testing. When you do everything full custom, you usually have a couple of them, and leveraging standards has really helped parallelize a lot of that development, and certainly there's a lot of reduced engineering time because we didn't have to invent everything, of course. So anyway, just a little bit of background there. As far as leveraging VPX at LANL, we've run into some interesting challenges, and certainly there's not a lot of, or maybe much at all, commercially SpaceVPX infrastructure for development and testing. Certainly there's lots of OpenVPX things out there. There's differences in the control planes in SpaceVPX and OpenVPX, so mixing them is a challenge. You have SpaceWire and Gigabit Ethernet over SerDes that certainly just don't talk to each other. SpaceVPX is very focused on fully redundant systems, and a lot of those, having it fully redundant really pushes, it exceeds our swap requirements and constraints for a lot of our designs. So that's an issue. And of course, if you just kind of went the OpenVPX route, you don't get some of the fault isolation recovery mechanisms in SpaceVPX. So we've been working on a system level approach that carefully hybridizes, OpenVPX and SpaceVPX. You'll see some of that shortly. And that gives us the ability to leverage more of the commercial hardware for development. Also gives us some of the fault isolation and recovery mechanisms from SpaceVPX, and reduces the swap of the systems. And so just a little bit of background on some of that experience. All right, so what's showing here is our first space grade single board computer, 6U form factor. Again, has some interoperability with OpenVPX and SpaceVPX. We took some particular slot profiles and tried to align those and take advantage of some of the commonalities there, so we can use this and both an OpenVPX and SpaceVPX context. The design goals, we want to be able to have this in GEO to LEO orbits, 100 kilorad TID, latch up immune, and mechanically hard, can deal with NASA GEVs or better shock, vibration, and thermal environments, conduction cooling. We're probably going to go with the HybridTAC connectors for the backplane. We've had a lot of success with those for other programs and previous systems, and all high quality components. And the low power, kind of like was mentioned in some of the previous talks, the great thing with the 740, you get some, certainly nice power and performance. And 8.5 watts for this board. Should mention that we've also licensed the 6U design to Cobham for their future uses. All right, so let's look at the initial 6U design. It's certainly attractive, the floating point performance. Our first design, based on the 740, the quad core performance, it's 250 megahertz for the processor core clock, and we've done some benchmarking that you can see that in some of our other publications, but we'll not go into detail here with that. This particular design has a gig of SDRAM, of course, with a half gig of EDAC to support error correction. It has 2 gigs of gigabytes of non-volatile storage, and has startup ROM, flash, and SDRAM memory hierarchy. The startup ROM for flight is we generally have used actual ROMs there, so that won't get corrupted. And then we have MRAM for kind of storage of the flight software, flash for other kinds of storage, and the SDRAM for software execution. We've been using VxWorks and RTEMS on these boards. And, because of the 740, we get a lot of great space grade sorts of interfaces with SpaceWire and I2C. We've added I2C, their discrete IO, and 1553 UARTs. And in this particular revision, we actually had, we leveraged the PCI interface for being able to interface to legacy CPCI boards. And so there's quite a bit of, we use, a lot of the capability of the 740 here. One of the things to point out, we're using an RTG4 as a companion device for the 740, and go into that in a moment here. So one of the things we use the RTG4 is to really provide us some flexibility and configurability for different missions, different configurations, and gives us a way to evolve things to from application to application. And so we're able to extend the IO standards and peripheral support for the single board computer. Again, I mentioned I2C, JTAG. To other boards, the multi-gigabit serial transceivers, we can leverage that way, and adding some additional memory interfaces, overcoming some of the limitations on the PROM IO bus. When it comes to needs for discrete IO, for example, like LVDS or single-ended IO, that can be programmed into the FPGA and given some flexibility, and meet those application needs. We've also been looking at using protocol-specific switches in the FPGA fabric to augment what's already in the 740. In this example, we've got a SpaceWire router augmenting what's in the 740 to give us, additional SpaceWire interfaces for redundancy and other purposes. And we've also looked at Ethernet options there. So with that on the bench, and we've been using it for a few years, talking to our internal customers and looking for opportunities for improvement. We've done a few things to the design. The internal customer didn't really need PCI any longer. They've decided to break from legacy there, so we've removed that from the design. The 1553 transceiver and magnetics moved to a separate board for modularity purposes there, and very similar to what we've done with previous systems, like with our GR740 design. Added 422 transceiver for the UART. We've added a microcontroller for state of health measurement and chassis management. And that way, some of the chassis management things don't necessarily have to be done with the 740. At least that's, we're kind of working through those details now, but that's new to the design. And as you can tell from some of the, the previous talk, we had to look at some of the memory and feature trade-offs, and I'll talk about those in a little more detail in the next few slides. This particular design went to 0.5 gig of SDRAM, of course, EDAC protected. We went to 384 megabytes of non-volatile storage, or reprogrammable non-volatile storage. And we've added additional Ethernet interface to help with development with the red tolerant PHY, so it could be flown if desired. So I'll go into some of those trade-offs here next. So with our original design, we had some 2 gigabytes of NAND flash, but for the things we chose, we were kind of limited to about 70K rad TID even after some extra screening. So internal customer really was, it was important for them to have radiation hardness, and so we over the storage density. I mean, the density would have been nice, but they prioritized that hardness over the density. So we started looking at some of the newer components there, and K's has a 128 megabytes of 300K rad TID NOR flash that's coming available soon, and so we've transitioned to that part. And so what we've done is we've got 256 megabytes of data storage, and that's behind the RTG4 due to some of the limited chip selects on the PROM IO bus for this design, and with the 740, and then we replaced the 8 megabyte MRAM with 128 megabyte NOR flash for the boot storage. So so that was driven by, again, by some of our internal customers' feedback. Now, as from the previous talk, SDRAM is kind of a and with packaging for space, right? All the different loads and things you have to deal with. We ran into an issue with the original design where there was some excessive loading on some of the chip selects due to packaging, and so it was limiting memory performance. And so we said, well, let's look at what's available and what else we could do here. So we looked at a couple of options. One was a 96-bit wide memory interface. Now, originally, that wasn't possible because of pin sharing with a PCI interface. Since there's no PCI in this design, it's something we could look at in the trade space. And so, at least of the options that we evaluated, this probably give us the maximum memory bandwidth and density. So 196-bit wide interface, gigabyte of ECC protected SDRAM running at probably pretty comfortably at 50 megahertz. Now, but because of pin sharing, you're really limited to a single SDRAM interface, and I mean not SDRAM, sorry, Ethernet interface. So that's kind of a downside with that approach. We looked at a 48-bit wide memory with some slightly different components and different package, and there again we have 48-bit wide interface. In this case, half a gig of ECC protected SDRAM. We're estimating, running at 70, 80 megahertz, based on current analysis. And so about half the RAM, about 70, 80% of that maximum memory bandwidth. But we get the benefit of an additional Ethernet port, so we can have one on the front panel for development and maybe for flights, and also had the option to run that to the FPGA, where we could use that to bridge into SerDes interfaces and host an Ethernet switch. And just given our current requirements, we've gone with option 2 there, and it's got a lot of memory. I mean, it's still an order of magnitude over our memory over what we did for with the GR740. So, and we get some additional connectivity. And just briefly, we also have a 3U design, and it's based on the original 6U design. It has the same amount of RAM. It has no startup ROM. We're relying just on the MRAM in this case, and for the booting actions there. And then it has half the flash of the original 6U design. There's, as you can see from the photograph on the lower right, not a lot of room for components. It's pretty full, so we had to trim back there. Again, using VxWorks and RTEMS with it. A lot of the standard interfaces, much like with our newer 6U design, the mill standard 1553 magnetics and transceiver kind of on a separate board as necessary. Yeah, but we still have some of these gigabit SerDes, multi-gigabit SerDes available that could be used for Ethernet, for high-speed, other kind of high-speed serial things. And in fact, with this particular design, we added a DDR2 SDRAM to support FPGA co-processing, and with an eye of maybe potentially supporting JESD 204B digitization interfaces directly from the FPGA. And so, bring some nice options for maybe better integration, smaller systems that way. So using the RTG4 a little more as a coprocessor. And it's kind of my final slide, just some additional kind of comments and summaries. But we, like was mentioned in the previous talk, the highest bandwidth interfaces from the 740 to the FPGA. Ethernet's the fastest. SpaceWire, of course, a really good another option. The PROM IO interface is really for low bandwidth control. We have the FPGA sitting on that bus, which is kind of different from our, with our 712 designs. The FPGA sat on a wider, faster, deeper memory interface. Sitting on the SRAM interface, and so that PROM IO interface is certainly limited, mainly kind of control. So you want SpaceWire or Ethernet to talk at high speeds between those two. And then having kind of reiterating, having that FPGA as a companion for the 740 has provided us a lot of flexibility, supporting different applications. It's reprogrammable, so that means that single hardware design can meet a lot of different needs from application to application. Gives us a way to bridge onto higher speed networks with SerDes, and extending some of the network protocol switching sorts of things on the SBC. All, of course, requiring some firmware development to do those sorts of things, but that's been a nice set of flexibility there. And final, the 740 has been a very reliable, productive basis for this generation of single board computers, and we've been pretty happy with that. So at that, I guess I'll turn the time back over.